Section 5.4, Calc 30, the second derivative test. So what is the second derivative test? Well, we talked about the first derivative test. You know about the first one, right? The first derivative test, we can test for max-min points. So we know that in the first derivative test, that if you have a derivative that's positive, and then 0, then negative, where the derivative is 0 there, you know that's a local maximum. And vice versa. So we took a look at that, I think in 5.2 maybe. The second derivative test gives us an indication. It's sort of a bit of a shortcut for determining max and min values. So it's another way to do max and min values, but where the second derivative is easy to attain in a polynomial, for example, the second derivative test is going to help us to avoid sign analysis. So that's the big plus for second derivative test. Let me explain how it works here. So far, the first derivative test, we have been able to determine local max and minimums been using sign analysis. So you don't have to write this down, but just to remember, you'd have factor 1 here, factor 2 here, whatever. Your first derivative was here. So you have your number line here, and you have different numbers here. And then you have signs of your derivative, right? And that sort of thing. And so you would be able to see that, for instance, if we had, oh, that was weird. Okay. If we had here a negative, the derivative was negative in this interval, then 0, then positive, that's a local min right here, right? This x value represents a local minimum. And so on. Positive, 0, negative, that's a local max. Negative, 0, positive, that's a local min, and so on. So that's the way we've been doing this so far. Well, there's a new way to take a look at this. But what we want to note from that is that at every local minimum, which would be sort of this case right here, right? That's a minimum and this is a minimum. At every local minimum, we notice that the concavity is always what? It's always concave up. You see that? It's always concave up. And I'll just draw kind of a corresponding parabola that fits in there. So it's concave. Cavity is, it opens up or it's positive. Right? So at every local min, the concavity is positive. And at every local max, like this over here, this concavity in this interval at this maximum, it's definitely in the middle of a concave what? Down. So that's negative. All right? So from one end of it, if you look at a local minimum, the concavity is positive or up. A local maximum has a local concavity, locally, it's concave down. So what's positive concavity? Well, that's a second derivative that's greater than 0. Right? It opens up. And concavity is negative when your second derivative is less than 0. All right, so if we notice that, and if you see that, then the second derivative test makes a lot of sense here. It says this: for every critical number, so you remember that critical numbers are where the first derivative equals 0 or is undefined. We are going to be able to examine those because that's where the local max or mins will happen. And we can determine whether it's a local max or min by evaluating the second derivative at each critical number. So for every critical number, we want to evaluate. And evaluate means we actually put the value of the critical number into the second derivative. So f double prime of c. And then we take a look at that. If f double prime of c is positive, that means it opens up. We have a local minimum. And that, of course, looks like this, right? Opens up. Well, here's your critical number, so that has to be a minimum. If you plug c into the second derivative and you evaluate, that means you find a number. And that number doesn't really matter what it is. The size of it, if it's negative at all, that means that that critical number has a local max. So if we have a critical number here and its concavity is down, it means we're going to have an f, a second derivative that's negative. So the positive of this is, well, I mean, it's good to notice these things, and just to discover this for the sake of discovery, for connecting the patterns in math and calculus. But also, practically, it erases the need for sign analysis in certain situations. So instead of finding the first derivative and then factoring, then doing sign analysis and the first derivative test, if it's not that difficult to find the second derivative, you just plug the c values, the critical numbers, into the second derivative and find out if the result is positive or negative, and then you know. So it's another way of determining. So let's go through this example together. Find local max and mins using the second derivative test. So this will be just like a question, on an exam that might come up, right? This is the basic thing. Find the local max and min using the second derivative test. So we have a function. This is a polynomial, right? Nothing too fancy. It's not a rational function. It's not going to be crazy. So I want to find the first derivative first to find the critical numbers. So step 1, find first derivative. Should be pretty easy at this point. Find the first derivative. From there, identify the critical numbers. So I'm going to let this equal 0, and I'm going to factor. I can take a 4x squared out, looks like. All right, and so that's going to be x minus 6. And so it looks like my critical numbers are x equals 0 for this factor, because 0 makes this one 0. And then x equals positive 6 for this factor, because positive 6 makes this 0. So our critical numbers are 0 and 6, looks like. Step 3, find the second derivative. And it is important to note that you do not need to simplify the second derivative. That's going to be really handy. Just one step of differentiation here, one step, that's it. You do not have to you have to simplify it. So y double prime then is going to be the derivative of this. Well, I could go back here. Derivative of this, I guess. Derivative of the first derivative. And so that's going to be 12x squared minus 48x. Okay. Now, I don't need to factor. I don't need to find 0 right now unless you're asked for points of inflection. But right now, we're just talking about finding local max and min. So notice, I'm just examining the critical numbers here. And our next step then is to plug the critical numbers into the second derivative and evaluate. And then we'll check and see what we have. So that looks like this. Y evaluated at 0 is going to be 12 times 0 squared minus 48 times 0. That's going to be pretty easy. That's 0. Okay. So 0. 0 tells us that we neither have, so the concavity is not up or down. It's not positive or negative. There's really no concavity there. So that is not a max or a min. Okay. So at x equals 0, not max or min. And that's okay. Probably going to be maybe a point of inflection, I guess, then, right? At that point. So let's check out 6. If we put 6 in. Okay, we'll zip that up quick on our calculator. So 12 times 36 minus 48 times 6 is 144. Now, the actual number doesn't mean much to us right now, but what does mean much is that it's positive. Okay? It's positive. So a positive number means that it's concave up, right? So what happens at x equals 6? That is a local what? Minimum. Thank you. So at x equals 6, and then y equals, whatever, you evaluate that, is a local minimum. Okay? And of course, you should figure that out, but we can do that real quick. So go back always to the original to find your x, y coordinates. Always go back to the original function, and we'll do 6 to the power 4. Okay, minus 8 times 6 to the power 3. Negative 432. Yep, I guess 6 to the power 4 minus 8. Negative 432. All right. Let's just check that. All right, that number checks out. Any questions about that at all? Might be a good idea to graph that and just kind of maybe see if we could confirm this. And actually, I will, because we should look at see what this zero means. So y equals x to the 4th minus 8x cubed. We graph that here. All right, so if we graph this, so I've graphed this off to the side here. Y equals x to the 4th minus 8x cubed. A little tough to tell. This is our 0 mark, right? Okay, so concavity changes there, but because it's a 0, it tells us that there's no maximum in there. All right, so concavity does change there. And of course, at x equals, what was it? X equals 6, we should have a local min way down at negative 432, which is going to be tough to see on this diagram. Oh, there we go. Negative 432. See that? Okay, so there we go. It's confirmed by our graph. So y equals x to the 4th minus x cubed. This is your turn now, so give it a try. I'll bring the steps down here too, so I'll show you the steps again. But find local max and or mins here for this question. Okay, so take the first derivative, find your, most of you have already seen this already. Take your first derivative, find your critical values, which would be 0 and 3/4. Find the second derivative, plug those values in. Now, 0, I could already tell in the second derivative that's going to be 0, so that's not going to help us. So you don't need to worry about 0. That's not going to be a local max or min. Okay? 3/4, you plug that in your second derivative, and you get a positive value. Therefore, it's concave up at that point, which gives us a local min at this point. Okay? So x equals 3/4 and y equals negative 27 over 256 or negative 0.105. Okay? And here's the graph to accompany, the graph of the original function. So at 0, you see we do not have a local max or min. It does change concavity, but it's not a local max or min. And that's what the y prime of equaling 0 will tell us. And then over here, it's concave up, so it is a minimum. And here's exactly 0.75 right here. Okay? So that's what you need to know here for this section. Are there any questions? All right, not a huge assignment here, so do a minimum that. If you get that done, please keep going. I did have 3D on my original assignment there, so we'll see. Anyways, yeah, actually, wait a minute. Why did I erase D? Let's see, yeah, D is actually on there. Yeah, D should be on there. So remember, if you need to watch a video, if you need to check out some homework questions, some of these, MrMathWell.com. Should be a D there.